Yes.
Hello, everybody. Today, our speaker is Luigi Caputi from the University of Turin. But he only spent more than 1 year a postdoc in Prague. And then he went to Scotland, right? And then returned back to now to Italy, and then soon be moving to Bologna. So he working on some very fashionable topics. And today he should give a talk on the spectral sequence, Mayer-Vietoris spectral sequence, and Überhomology. Überhomology is completely new subject. When I saw such a terminology, I'm very surprised and asked Luigi explained it, but he should explain us today. Yes, please.
Thank you very much. Yes. It's thank you very much for the invitation. It's always a great pleasure to be back in Prague. And first of all, yes, Überhomology is not my creation. So this was developed by Daniele Celoria a few years back. But this is a joint project where indeed Daniele Celoria and Carlo Collari. Is it visible? Yes. Yeah. And Daniele Celoria in Melbourne, Carlo Collari in at the University of Pisa. So the plan of today is to describe basically Überhomology in terms of the second page of this of a certain spectral sequence, the Mayer-Vietoris spectral sequence. And before going to that subject, I think also to right? Okay, sorry. Okay, to have the common terminology, I would start since the very beginning. So please to ask questions if you have. And the very first thing I wanted to say is that, okay, if you have a topological space, how to describe the Mayer-Vietoris spectral sequence? If you have a topological space X and you have two open sets A and B, so such that the intersection is non-empty, then we know that there is a long exact sequence that allows us to compute the homology of X in terms of the homology of A, B, and the homology of the intersection. So the question is, what happens when we have more covers? So a cover that's bigger than two pieces. So we have, for example, X simplicial complex, and Y a simplicial cover. So by this, I mean that all the UIs are going to be subcomplexes of the complex X. And here everything is finite. And also I is assumed to be finite. So if we have such data, in the case of the long exact sequence, we have only A and B. If we have a bigger cover, then we have not just the long exact sequence, but we have an entire spectral sequence. So how do we construct it? So just as a notation, for J included in I, we denote by Uj the intersection of a J in J of the Uj as a notation. So, and we also put as a convention union of the empty set to be X. So now if we have this data, we can construct what's called a nerve. Over here. As you might know, this is the simplicial complex. On the set of vertices I is the index set of the UI with, so let me write on J in I such that Uj is not empty. So this is a simplicial complex because I'm putting in this relationship. And then as an example, if we have X, that's this simple complex, let's assume that we have vertices V0, V1, V2, but we can here, for example, take here as first subcomplex A. So A is V0, V1. The second one, V1, V2. It's pretty clear that the intersection is non-empty. It's V1. And the nerve of the cover given by A and B is the standard simplex delta 1. But if I had chosen a different cover, so let me say that U0 is the anti-star of V0, but the anti-star, I mean that I'm taking the subcomplex of X obtained by removing V0. So V1, this is V1, V2. So U1 is the anti-star V1, V2 is the anti-star V2. Then you can see that the nerve of this cover is not delta 1, but this is this time S1. So if we start with the topological space, we might get different nerves. Now should I go to another blackboard or?
Yes, you can go to another blackboard.
Ah, okay, good. So we have different nerves. They are non-homotopic, so they're giving to us different information about the space. However, we're gonna see that the spectral sequence is gonna converge still to the homology of X. Right? Yes.
X is just a collection, finite collection of just one. So, and the cover is trivial. So each piece of each U
Yes.
just covers just one point. Then all intersections are going to be empty, so the nerve is going to be
Just a bunch of points.
okay, one element of I are going to be okay.
Yes. Okay, so this is to say that if you start with the same X, you can have different non-homotopic even nerves, but still the spectral sequence that we're gonna now describe is gonna converge still to the homology of X. So we said that we have a simplicial complex. U is our prime cover, we have our nerve. And what we can construct a bicomplex. So CPQ is given by the sum over all, let me write like all simplices of the nerve of U in UFP of the Q chains of U sigma. Where by this, I mean so there is a correspondence between the subsets of I, the J, and the P simplices of the nerve. So I'm always gonna switch between the two notions. I brought the nerve, the sigma in nerve of U, I'm always mean subset of P+1 elements. So I'm associating to it this sum, but obviously here there is a differential, the vertical differential that goes to the Q-1 chains, and this is using the differential of X, let me say. But there is also another differential that's induced by the nerve. This goes to Cp minus 1, Q minus 1, Cp minus 1, Q, and this is the vertical differential. Clear? Good. So this can be extended, and we have a bicomplex. What happens if we first take the vertical differential, we obtain the homology of the sigma, And this is gonna give us the one term sum sigma of the homology of E sigma. We still here have the P differential going from E1 PQ to E1 P minus 1Q. We started with the vertical differential. Okay. Any question?
Okay.
Yes. So I'm just saying that I have the vertical differential that's induced by
Yes,
the.
but I don't know how to accept the good thing about the first kind of complex associated to that simulation cohomology complex. That the EU or that classical stuff.
This is the classical step. Yes. Now, just saying that I'm starting with we're taking the vertical differential first, and then now I want to take the horizontal one.
Yeah.
So I got a spectral sequence, which is classically called the Mayer-Vietoris spectral sequence, converging to the homology of the total space, which is the homology of X. And by using this, one of the classical results is the nerve lemma. So the nerve lemma says that if X is a finite simplicial complex, and U is above, with the condition that U sigma are contractible sigma, then the homology of X is going to be the homology of the nerve of U. So we can see here that in this example, what we had first, we had contractible intersections. So the nerve is that the one which is whose homology is the same of X. But in this case, this is not true because one of the intersection is S naught. So this nerve lemma works because of this condition. That's usually said that the cover is good. If we have simplicial complex and you have a good cover, then the homology of X is the homology of the nerve. However, so the natural question comes and, yes. Should I move here?
No, you can.
I can.
Yeah.
Okay, thanks. So the nerve lemma has been used for many different fields. We're not going to discuss it here because it's really an incredible subject. But the main question that I want to ask here is that what does it happen if the cover is not good? So basically, what can we say about the Mayer-Vietoris spectral sequence? So we know that the Mayer-Vietoris spectral sequence is still converging to the homology of X. So all these pages of the spectral sequence are going to give us some approximations of the homology of X.
So what means good cover?
The good cover, yes, is a cover for which all the intersections are going to be contractible.
Yes. So
if you have this condition, then basically the spectral sequence is going to give us the nerve lemma. So the question is that if U is a cover, simplicial cover of X, then what topological or combinatorial information can we read from its pages? So this is a very vague question, but it's motivated by the fact that if the good cover, if you have not good covers, what can we still say? This is the question, and our partial answer is that if we restrict to U being the n-tile cover of X, so meaning that all the subcomplexes are obtained by deleting one vertex, but taking all the different intersections, then the second page of the Mayer-Vietoris spectral sequence is isomorphic to the 0 degree of Überhomology. So even if the cover is not good, we can say something about the second page of the spectral sequence. And this is the motivation of this work. Questions? Yes.
Does converge to the actual homology?
Yes.
No,
no, you do not assume that. So the spectral sequence is always going to converge, because the reason is that if you start from this bicomplex first by taking the horizontal differential, then the rows are going to be acyclic. And the second page is already the homology of X. But now you turn out, but now you start with the vertical differential, and then you with the horizontal differential, and then you should get again a spectral sequence that converges to the same object, the total complex. And this is a merge of X. What can be said can be read off from the second page, the spectral sequence. And in this specific case, we can say something. Okay, so let's discuss a bit of Überhomology. So this is a triply graded homology theory of simplicial complexes. Triply graded, we will see why, which is, so it was defined by, so we'll say, Celoria a few years back. And its definition is based on the pi colorings on the topological space, on the simplicial complex. And it is reminiscent in some sense of the Cohomology homology. And we will see why. It is a poset homology, in short. So let me first give a definition. X be a simplicial complex. Then a bicoloring on X. It's just a say epsilon in the vertices of X to 0, 1. So we can consider pairs X epsilon, so call them bicolors. Simplicial complex. I fix a simplicial complex, and then I consider a bicolor on it. So for sigma P simplex, I can define what is its weight. So sigma has vertices which are colored by this map is 0, 1. So definition, the weight of sigma is basically the sum of the 0 colored vertices in sigma. So this is the quantity without the epsilon of sigma given by the dimension of sigma plus 1 minus the sum of vi of epsilon of VR. And the vi are running to the vertices of sigma. So let me plot a picture. This. So for example, if we have this simplicial complex, I don't know. So this is a two simplex. We have two vertices colored in 0, so its weight is going to be 2. But here, this is also having weight 2, but this is weight 1. So we're only counting the number of zeros in the picture. The point is that we can use this weight to filter the chains of the simplicial complex. But the weight induces a filtration of the chains on X. How do we define Fj of X with respect to epsilon is generated by all sigma for which the weight of sigma is bounded by J. The differential is going to be preserved, and this gives you a filtration of these objects. So the differential is preserved, but we actually have two components. So let me call delta this differential. It has two components. Let me call it delta H and delta H bar, where delta H is the component of the differential that preserves the weights, whereas delta H does not. So for example, if we have this simplicial complex and we're taking delta, so let me call this V0, V1, well, delta of E is going to be in F2 coefficients. It's going to be like V0 plus V1. Well, V0, which is colored by 0, is delta H of E, and this is delta H bar of E. So I can decompose the differential with the two components, the one that preserves the weight and the one that does not. So in this picture, we're gonna forget about the differential that does not preserve the weight.
What is motivation of such kind of filtration and coloring?
This is
completely clear.
I think this is a question that we should be asked to Daniele.
No.
What was his motivation? I think I have no idea. No, but the homology theory that goes out, it is pretty clear. So, and we shall see. So basically, the idea is to decorate the Boolean poset of all the possible bicolorings on X with the homology that we obtained this way. So what kind of combinatorial information can we get out of it? So, and in fact, what I wanted to say, yes, if we have X and epsilon, a bicolored simplicial complex, by considering the horizontal, let me call it a horizontal differential, then we get what we call horizontal homology. So this is the homology of the star X epsilon with respect to the H. Okay. So let me give some examples. So first here. So the point is that by coloring in different ways the vertices of X, we're going to focus basically on subcomplexes of X. So if we color everything with 0, what does it happen? So let's see. If we have the same pictures before, so we have our edge with two vertices B and 1, and let's say that these are both colored in 0. So let me put here the simplicial dimension, and this is the weight. So yes, I forgot to say the horizontal homology, this is bigraded. And it's bigraded both in the simplicial dimension and on the weight. If we put here, we have of weight 2 and simplicial dimension 1, one single object, E. But of dimension 0 and weight 1, we have the two vertices, V0, V1. The differential here is 0 for both. So what do we get? We get basically that E, V0, and V2 are components of the horizontal homology. So if you want the horizontal homology of X with respect to this epsilon, is nothing but the sum of the chains of X shifted by k plus 1 to take the degree into account. What happens if, let me go here. What happens if instead of coloring everything with zeros, we're going to color everything with ones? Any? Yes, what's the information that we get? Do you have any clue? What do we get if we color everything with 1 and we compute this guy? Well, let me check again. So here everything is colored with 1. So they are all in weight degree 0. E is in degree 1 here. B0 and B1 are in degree 0. And the differential is the usual differential. So what we're getting here is the standard homology of X. So by going from this completely zero colored simplicial complex, which gives us a combinatorial information about the simplicial complex, meaning we're summing up basically all the simplices composing the simplicial complex, we are going to the classical homology of X. So all the other steps, maybe this answers the question, all the other steps are intermediate. We're gonna get like an approximation or further approximations of the homology of X in combinatorial terms. So the other example, for example, was the one over there. So here, B0, B1, this is 0 colored and this is 1 colored. What happens here? Well, this is, E is a weight 1, but also V0 is weight 1. And the differential sends E to V0. V1 instead is here. It is 0 dimensional as a simplex, but it's also 0 dimensional as a weight. So the horizontal homology is going to see only V1. And this is a remark. The 0 degree of the horizontal homology is the simplicial homology of X epsilon, where with X epsilon, I mean X generated by all Vk such that epsilon Vi is equal to 1. I take the subcomplex generated by ones, and I compute its homology. This is the horizontal homology. So all this, yes. ask me again?
They have two very close colorings. Like one
Yes.
color is different from another.
Okay.
Color. So
Yes.
They're going to be related by in the letters, in the wooden letters, they're going to be just
Yes. One cover to by the other.
So
Yes.
how can we relate the horizontal homologies? Because once we anticipate that they belong to they will different by something.
And this is a very good question, and because it is anticipating my next the next operation. Indeed, thank you. No, there is a map between the horizontal homology of x epsilon colored with the horizontal homology of x epsilon prime colored. There is an induced map, and this is indeed the case. So what I wanted to say before going in the direction is that so far we focused on a simplicial complex with the choice of a singular bicoloring. Now we want to take all of them into account. So what happens? What happens if epsilon is covered by epsilon prime? As I was saying, there is a map connecting the two. But this means that horizontal homology can be seen as a functor on the posets of all bicolorings of X. So let me write it. So let's say that epsilon is covered by epsilon prime if epsilon bi is equal to epsilon prime of bi for all I different from k, and epsilon of vk is equal to 0, epsilon prime of vk is equal to 1. So the lemma is that in such case, epsilon is covered by epsilon prime, then there is a map. From the horizontal homology of X to the horizontal homology of X with respect to epsilon prime. So this is compatible. It gives us, let me write it like this. If Bm is the poset of all possible bicoloring of X, where M is the number of vertices, so it's given to me epsilon, I'm going to give to you the horizontal homology of X with respect to epsilon. So this is a functor. Well, the first definition is that we write like this: Überhomology is the poset homology of the M of the Boolean poset with respect this functor. So if you don't know what's poset homology, I'll give you. Yes, I'll give you the definition. Oh, yes. So what do we have here? We have a Boolean poset. What?
Yes, okay. I see.
Okay. So okay, well, so we are at this stage. So we have for each point, for each object of a poset, we have a decoration, the graded module given by the horizontal homology of X. For each map, we have a map of graded modules from the horizontal homology to the horizontal homology of X. Now we define, so this poset homology says that define the chains to be consistent, J, X to be the sum over all epsilon of length J, where by length I mean the sum of the one entries in epsilon. So length of epsilon is the sum of epsilon I. I count how many ones are here. Of what? Of the horizontal homology of X epsilon. So this is gonna be the chains, and the differential is gonna be defined as homological gradient. I'll give you a picture because otherwise it's a bit unclear. So the picture, for example, let's take delta 1, so the one simplex. We have the 0,0 colored simplex and its horizontal homology. We have a map to the horizontal homology of 1, 0. A map to the horizontal homology of X decorated this way, and then we have the maps to the horizontal homology of delta 1 decorated with all ones. What are we doing here? Okay, here, this is the first chain group. We take the directed sum here, and this is the first chain group. And here I sum up over F2 the differentials. I get the differential here. This is C2. And I take this, I sum up the differentials. Yes, I suppress this. Yes, because I'm considering them all. Yeah, this was supposed to be an H, sorry. So in the positive fashion, I'm looking at, epsilon of length 0, length 1, length 2, and so on. I sum up column-wise, and I take the induced differential. The Überhomology of X is going to be the homology of this chain complex. In the meanwhile, any questions? Yes, I show you in the concrete example this one. So let me write it as I wrote before the weight and the simplices, because okay, I have them there. So in the first case, I had a class E, and I had two classes, V1 and V2 here. Then in this case, this is 1, 0 colored. So I have, okay, what is V0 and V1? Let me say V0 is this one, V1 is this one. So in this example, E is gonna cancel out V1, so I got V0. And E is matched with V1. Here is matched with V0, and I get only V1. And I have here E that goes to V0 connected V1. So now the differential of this is weight 1, this is weight 2, this is weight 0, weight 2, sorry, weight 1. So the differential should preserve also the weight. So these are gonna go to 0. This one goes to the class generated by V0 or V1, they are homologous. This one goes to the same class. So here I had, let's say, a copy of F. This is a copy of F2. This is a copy of F3. This is 0. This is the 0 map. This is the plus map. This is 0. And then the Überhomology here, the Überhomology for X is going to be F3 in degree 0. Everything goes to 0. And the Überhomology in degree 1 is going to be F. There's no homology here because we got it. Yeah. Is this example satisfying? So I can't sit here.
So
Yes.
that's really, when you say about the cohomology, you only give that what information is preserving. Yeah. So that's when you coloring, that's how I mean every color gives some completely different.
Yes. Information. Yes. And as you can see from the 0 colored simplicial complexes that had only a combinatorial information, we're going to the 1 colored simplicial complex that has a topological information. In between, there were all these different colored information. And this poset homology is trying to pack them up in a global object. So what is happening here is that basically you have a simplicial complex, the nerve of the bicolor, of the Boolean poset corresponding to all the bicoloring, and you are taking the local coefficients with respect to the horizontal homology. So for each bicoloring, you're considering the horizontal homology as a local coefficient system, and you're packing them up in a global object. That's the homology, the Überhomology. Let's see some computations. Before that, just as a notation. So we have a triply graded homology theory. This is the homological degree.
So let us try to make some very simple play. Usually you keep refining complex, yeah.
Yes.
So then how you think that's how I make the new coloring that the same cohomology happen? Or I mean
It may happen. It may happen.
But can you have some theorem that if I refine the complex, then of course the cohomology.
Yes. Yes.
So now it keeps the coloring on the thing, and how I color the new thing to make the.
In the horizontal homologies, you can use something that you will see these maps obtained, but in the global objects, that's a bit more trickier. We will see, for example, that for barycentric subdivisions, there's going to be everything 0, but in other case, we can say something else, and we will see. Yes.
It's something information.
Yes.
He's saying that is the object study. If everything is not then.
Yes, yeah. I show you. So first of all, okay, let me say that basically two results. So that so what happens in the bottom degree, the 0 degree, what happens on the top degree? So this is only Daniele. All this construction was for Daniele. So if X is a simplicial complex, so as we know, then the bottom degree of Überhomology is going to be the sum of a J of F and J, where Nj is the number of J simplices in the intersection of all the closed stars of the vertices. So as you can see now, the stars are appearing, they were appearing at the very beginning, and I said that there is a relation with the star of simplices, and in the bottom degree, we can see that this is the case. What happens in the top degree? So if, say, X is a triangulation of a closed manifold, then.
Sorry, Luigi, you are out of the camera, probably.
Am I?
I don't see you, but maybe I'm
Ah,
frozen. I don't
here.
know. Oh, probably not.
What is the problem?
the time it's focused on the mid camera. Thank you. Yeah.
Yes, it's okay.
Okay, thanks. So I was saying, so the 0 degree homology is basically generated by the synthesis and the intersection of the stars. But if X is a triangulation of a closed manifold, then the top degree, so M is the number of vertices of X, and the top degree is F. And this is generated by the fundamental class of X. So we see that in the bottom case, we have the combinatorial information again. In the top case, we have some topological information. And the question is what happens in between. In order to, I can stay here. So the point is that in general, we don't know what happens, what is Überhomology saying. But let's first focus on the 0 degree part. So we have Hjik of X. We reduce it, put in the weight degree to 0. We get another bigraded homology theory. And then we reduce it again to be simple. Then we put I equal to 0. This is the simplicial degree. We got something that was called homology. So just an observation. We focus now only on the 0 degree part of Überhomology. What can we say? Well, the first lemma is that if X1 is the one skeleton of X, then Hj of X is nothing but Hj of X1. The Bode homology of the simplicial complex is the Bode homology of the one skeleton. So we can reduce only to graphs. And as we are restricting to the case of the 0 degree case, if you remember the very beginning, I was saying that in the 0 case, the horizontal homology is actually the classical homology of the one-colored sum complex. So we have a simplicial complex. We are only looking at the one-colored simplicial complexes, but only the 0 degree part, simplicial. So we're only looking at the connected components of those. So let me recall some definition. Let S be a subset of the vertices of G. We say that S is connected if it spans a connected subgraph. And we say that's dominating if its one neighborhood generates the graph. Let's say the neighborhood of S is equal to G. So everything is close, one close to S. What's the relation with Überhomology? The relation is the following. That define dCg of X to be the sum of all S in the vertices of G, which are connected and dominating, of X to the cardinality of S. This is called the connected domination. Polynomial. So we have a graph. We are focusing on the graphs because the 0, 0 degree part of the simplicial complex is actually the same as its graph. We can only consider the connected dominating subsets of vertices. Take the polynomial. The theorem is, that mod homology is categorification of the connected domination polynomial at minus 1. What does it mean? It means that if I compute the Euler characteristic of the mod homology of a graph, then this is the connected domination polynomial at minus 1. So this is capturing some combinatorial information of the graph. And this is
Yeah, correct.
yes, together with. So this is, I think, basically, out of this, we can have some computations done. At least we can understand pretty much of the 0, 0 degree of Überhomology, because the point is that it's not just a categorification, but the Uber chain complex is now quasi-isomorphic to the chain complexes obtained by looking only at the connected dominating subsets of the graph. But pretty much combinatorial information. Yes.
What does span mean? Particular why?
Yes, sorry. So here, I mean that I have a graph. I'm taking some vertices. I take the subgraph spanned by these vertices.
Okay, so dominating means
The dominating means if I take now any edge, any vertex in G is either in S or is adjacent to a vertex in S. So there is an edge connecting it to itself or to another vertex in S. So for example, if G is Kn, the complete graph on n vertices, then any D is connected and dominating, because everything is one close to one vertex. So, and this, some properties, well, this H1G is F, yeah? Well, it's different from 0 if and only if G is isomorphic to a complete graph. Or if G is a tree, then the mod homology of G is complete with 0 and so on. So we have some understanding of the 0, 0 degree part. So in this reduction, so we understood roughly the 0, 0 degree part, so we can come back to the, let's say, k equal to 0 part. So to the 0 degree part of the Überhomology. And this is the guy that's going to be isomorphic to, as a graded object, to the second page of the spectral sequence. Yes?
the G is a key to vertices on one edge.
I'm not saying that's directly straightforward. By using the dominating subsets, you can prove these things.
What I meant was that K2, the complete graph is two vertices, is also is a tree, right?
No, it's not contractible. No, sorry. You're totally right. That's not delta one. Yes. Luigi, thank you very much. Yes, very good observation. So in order to understand what happens to the 0 degree part, let me define the augmented spectral sequence. Augmented spectral sequence with respect to the cover given by the anti-star covers is spectral sequence with E1 term some sigma in the nerve yes as before, but at -1 position we add the homology, the Cohomology of X. So we get also the differentials of hitting this. The second theorem that I wanted to present is that if X, so this is again should be finite as always on n vertices, then there is a bigraded an isomorphism of bigraded modules which gives us the second page, but in degree n minus j minus I, sorry, n minus j minus 1, comma I is b j I x. So there is an isomorphism between the groups appearing in the second page of the augmented Mayer-Vietoris spectral sequence and the groups, the Überhomology groups in 0 degree. What's the idea? Of this? Well, the idea is now to compare first this E1 term to all this Überhomological description that we have. So in order to do that, first observation, we are focusing or we are restricting to the case of the 0 weight. So I was saying before, if we are restricting to the case of the 0 weight, then the horizontal homology of X epsilon is the homology of X epsilon, where X epsilon is the induced simplicial complex on D1, VI1, VIK, or VIS equal to 1. So I'm only looking at the one colored subcomplex. So this was the classical homology, but also this is X epsilon. The other observation is that can be described as the intersection of the anti-star of the VI, where let me call it T, where T does not belong to I1, IK. So either describing the induced sum complex on the one colored vertices or describing the intersection of the anti-star is totally equivalent. So first observation is this. The second observation is that the differentials are also going to be preserved. The differential in this description are also going to be preserved. So I have the maps connecting the horizontal homology of X with homology of X epsilon prime. This is the homology of X epsilon, and we have the homology here, X epsilon prime. But this is the homology of the intersection of the anti-star. This is the homology of the intersection of the anti-star. Well, but then now the second step in the computation of the Überhomology, oh, it's not there anymore, was to sum up all these horizontal homology groups, right? So we have the E1 PQ as the sum of sigma of the homology of U sigma. But the homology of U sigma is the homology of the intersection of the anti-star, which is the homology of X epsilon. This is E1, so this gives us that E1 PQ is giving to us the qth component of the Überhomology. Basically gives the Uber chains. The last step is that I take the differential. We take the differential, and then we get the formula. And this concludes basically the theorem. I think I'm over time of a couple of minutes, but I think I can stop here.
So just 10 minutes on the problem.
Okay, also 5 we want.
Yeah.
So to at least discuss a couple of direct applications. So because now we have understood that this Bij is related to the Mayer-Vietoris spectral sequence. So we can use the topological informations on X to infer properties on Überhomology and vice versa. Let me remind you that. So recall, let's see what the complex. X is called the array if the reduced homology of all induced subcomplexes of X is 0 in degree bigger than B. So we have the ith homology of X is 0 if I is bigger than B. And this is telling us what the Diehl-array simplicial complex or CW complex is. U simplicial cover of X is Diehl-array if all its components are Diehl-array. Well, it is clear that if we're using the Mayer-Vietoris spectral sequences argument, we are looking at all these induced subcomplexes of X. So this is a condition that helps us in the computations. And for example, position, if X is not the standard simplex, but it's connected, contractible, one array, then the Überhomology is completely trivial. So this is a combinatorial gadget that's actually capturing some information also of X. So if it's contractible one array, then everything is 0. On the other hand, if this is a bit more complicated, if X is still connected and one array, then what we have is the -1 to the number of vertices of X. So I'm taking the evaluation at -1 of the connected domination polynomial of the one skeleton of X. This is the characteristic of X -1. So there is this correspondence between the connected domination polynomial of the one skeleton and the other characteristic of X. So for example, as a corollary, if you have the if you have a graph which is chordal, which means that all the cycles of length at most 3, then this connected the characteristic is 0. This is going to be the connected domination polynomial at -1 is going to be 0. So you know that -1 is root of the connected domination polynomial, and finding basically the roots of the connected domination polynomial, or finding the connected dominating set, might be really hard. So this is, I guess, too much over time. I think I might stop here. Yeah,
Thank you very much. Yeah.
Thank you.
So, is there some application like to persistent homology or topological data analysis?
Not yet. Or maybe there's gonna be some, but this is pretty much related as well, because it's gonna use filtrations of simplicial complexes and all. Let's see.
Yeah.
Let's see. This.
So we got two color.
Yes.
Color. That's for 1, 2. So there seems to be a way to form a coloring on the product. You just consider them as like vectors multiplied.
Yes.
Using a metric of time that you want.
Yes.
So is there some kind of
I don't know yet, but that's not unlikely. Because if I look at this, the 0 degree or the 0 degrees related to this Mayer-Vietoris spectral sequence. So if this allows you to use the product in the spectral sequence, that's totally all right. I don't see any obstruction at the moment. So I forgot to say that everything here was now about the 0 degree. Here at this level, that's not clear what the Überhomology is saying. And also what is the meaning of certain classes or characteristic classes, how to get, many other questions out there.
So then the guy who invented Überhomology, what is his main theorem or not main? It's like that what's the motivation or?
Its motivation, I think it was to understand better triangulations.
Yeah.
So as you said, so before this, so if you have a simplicial complex that's a triangulation of a manifold, of a closed manifold, then you can find also this fundamental class there. And this, we're working on that direction as well. We're trying to understand what's the relation to triangulation and whether we can say things about that. So this is the main motivation, I would say.
So I think that you proved my theorem about this homology, right? The Überhomology is related to spectral sequence, and the guy invented this Überhomology. What did he prove?
He proved all the first part that I showed, all this construction, all these things.
Yes, but you can define some iteration and
Yes,
the
yes,
output.
and then much more things that I haven't said here because of that obviously time reason.
Okay. Is there more some question? So if not, then
Maybe. Oh no, maybe not. No.
yes. If not, then let us have a speaker.
Yes.